The fundamental currency of our universe is energy. It lights our homes, grows our food, powers our computers. We can get it lots of ways: burning fossil fuels, splitting atoms, or sunlight striking photovoltaics. But there's a downside to everything. Fossil fuels are extremely toxic, nuclear waste is, well, nuclear waste, and there are not enough batteries to store sunlight for cloudy days yet. And yet, the sun seems to have virtually limitless free energy. Is there a way we could build a sun on Earth? Can we bottle a star? The sun shines because of nuclear fusion. In a nutshell, fusion is a thermonuclear process, meaning that the ingredients have to be incredibly hot, so hot that the atoms are stripped of their electrons, making a plasma where nuclei and electrons bounce around freely. Since nuclei are all positively charged, they repel each other. In order to overcome this repulsion, the particles have to be going very, very fast. In this context, very fast means very hot. Millions of degrees. Stars cheat to reach these temperatures. They are so massive that the pressure in their cores generates the heat to squeeze the nuclei together until they merge and fuse, creating heavier nuclei and releasing energy in the process. It is this energy release that scientists hope to harness in a new generation of power plant, the fusion reactor. On Earth, it's not feasible to use this brute force method to create fusion, so if we want to build a reactor that generates energy from fusion, we have to get clever. To date, scientists have invented two ways of making plasmas hot enough to fuse. The first type of reactor uses a magnetic field to squeeze a plasma in a donut-shaped chamber where the reactions take place.
You ever seen Iron Man?
These magnetic confinement reactors, such as the ITER reactor in France, use superconducting electromagnets cooled with liquid helium to within a few degrees of absolute zero, meaning they host some of the biggest temperature gradients in the known universe. The second type, called inertial confinement, uses pulses from superpowered lasers to heat the surface of a pellet of fuel, imploding it, briefly making the fuel hot and dense enough to fuse. In fact, one of the most powerful lasers in the world is used for fusion experiments at the National Ignition Facility in the US. These experiments and others like them around the world are today just experiments. Scientists are still developing the technology. And although they can achieve fusion, right now, it costs more energy to do the experiments than they produce in fusion. The technology has a long way to go before it's commercially viable, and maybe it never will be. It might just be impossible to make a viable fusion reactor on Earth. But if it gets there, it would be so efficient that a single glass of seawater could be used to produce as much energy as burning a barrel of oil, with no waste to speak of. This is because fusion reactors would use hydrogen or helium as fuel, and seawater is loaded with hydrogen. But not just any hydrogen will do. Specific isotopes with extra neutrons, called deuterium and tritium, are needed to make the right reactions. Deuterium is stable and can be found in abundance in seawater, though tritium is a bit trickier. It's radioactive, and there may only be 20 kilograms of it in the world, mostly in nuclear warheads, which makes it incredibly expensive. So we may need another fusion buddy for deuterium instead of tritium. Helium-3, an isotope of helium, might be a great substitute. Unfortunately, it's also incredibly rare on Earth. But here, the Moon might have the answer. Over billions of years, the solar wind may have built up huge deposits of helium-3 on the Moon. Instead of making helium-3, we can mine it. If we could sift the lunar dust for helium, we'd have enough fuel to power the entire world for thousands of years. One more argument for establishing a moon base, if you weren't convinced already. Okay, maybe you think building a mini sun still sounds kind of dangerous. But they'd actually be much safer than most other types of power plant. A fusion reactor is not like a nuclear plant, which can melt down catastrophically. If the confinement failed, then the plasma would expand and cool, and the reaction would stop. Put simply, it's not a bomb. The release of radioactive fuel like tritium could pose a threat to the environment. Tritium could bond with oxygen, making radioactive water, which could be dangerous as it seeps into the environment. Fortunately, there's no more than a few grams of tritium in use at a given time, so a leak would be quickly diluted. So we've just told you that there's nearly unlimited energy to be had at no expense to the environment in something as simple as water. So, what's the catch? Cost. We simply don't know if fusion power will ever be commercially viable. Even if they work, they might be too expensive to ever build. The main drawback is that it's unproven technology. It's a $10 billion gamble, and that money might be better spent on other clean energy that's already proven itself. Maybe we should cut our losses. Or maybe.
Pretty interesting stuff, right? Pretty crazy. Is it worth it? Will it be worth it? Will we ever know? That's the question. We don't know. Okay, so fusion. Two things fusing together just like the sun. Is that a good reminder? Good video? I like the sun in that one, right? Now, what is fission? What is fission? So we're going to knock this out real quick. I've got a pen. There we go. So we are on number 4. Okay. Now number 4 is what we already know. We know how to do fission. We have a nuclear reactor here in the state of Ohio. How cool is that? Okay. So question number 4, what is nuclear fission? How does it happen? What is nuclear fission? And it's just not worth it. Yeah, it's worth it. It's worth it. That's gonna bother me. 4th tries the charm. 5th tries the charm. 6th tries the charm. Golden. All right. Let's see. Releasing. So what is nuclear fission? Releasing the energy of an atom by breaking a large unstable nucleus into smaller particles. Okay, so fusion was putting two things together. Fission, breaking them apart. Okay, we're just breaking things in half. Okay, if you turn your paper sideways, fis stems from the Latin. From Latin, it means to split. Okay, means to split. All right, what else do we got? Takes place, where would that be? Oh, at the very bottom. Takes place in nuclear power plants and the atomic bomb. So, kind of crazy how we're powering houses with the same energy that could blow them up. Is that smart? I don't know. All right. So what does it look like? Can I move on? We good? So what does this look like? Okay, so what it looks like is you bombard giant unstable nucleus with a neutron. Okay, so we're hitting a uranium atom with a neutron. Boom. Okay, we're hitting the uranium with a neutron, and what results is barium and krypton. Okay. And lots of energy. Bless you. All right, so the uranium breaks into barium. You can just put barium and krypton. You don't need the numbers to go with them. Barium and krypton. Okay. Plus 3 neutrons and lots of energy. 3 neutrons and lots of energy. Okay. Now, the question on the paper says, what do you think happens to those 3 neutrons? So we create 3 neutrons and lots of energy. Well, what happens to those neutrons is, what happens to those neutrons? They hit another uranium atom. And that uranium breaks into barium, krypton, lots of energy, and more neutrons. And then those neutrons hit more barium or uranium and create barium and krypton. And the cycle continues and continues. And that is a chain reaction. Okay? All right. Now, the crazy thing about fission, so we went over we talked about some negatives. But what are some positives? Okay? The positive is a baseball-sized amount of uranium has the same energy potential as 1 million gallons of gasoline. 1 million gallons of gasoline is the same as a baseball of uranium. That's pretty wild. That's huge. 1 million gallons compared to a baseball. The problem is it produces waste. All right, so way at the bottom, fission produces waste. All right, way at the very, very bottom. Crazy stuff. So there's some benefits, creates lots of energy, doesn't require much waste. But now, where do we store that waste? If it creates radioactive waste, what do we do with it?
Put it in the ocean.
Not quite. So what? That's been discussed, yes.
That would be incredible.
We actually dig a hole underground, put it in a barrel, and leave it there. That's what we do. It's the best option right now. We have no other option. The other option is the moon, right? In all seriousness, that's the other option. So, do we kind of have an understanding of fission? All right, so a neutron hits uranium, and uranium breaks into barium, krypton, and 3 more neutrons with lots of energy. We feel good on that? All right. What is a chain reaction? This is going to be a kind of quick one. All right, next question, number 5. Number 5 says, what is a nuclear chain reaction? Okay. So we're going to watch a quick video. I'm pretty sure both of these boxes you can fill in 100. Okay. The number of dominoes is 100. Okay. So this science teacher set up a domino experiment, which is awesome. I just didn't feel like setting up all these dominoes. I'm not that good at setting up dominoes.
I'm really good at it.
Really?
Mm-hmm.
I don't
We're
know.
going to demonstrate 2 different things here today. We're going to demonstrate a chain reaction, but basically 2 ways. Now, usually when you think of a chain reaction, it starts and then it keeps on going. It's self-sustaining. But when you're talking about nuclear fission, which is the splitting apart of a very large nucleus into smaller nuclei, the chain reaction can be of several different types. And so what we're going to do is demonstrate, first of all, what's called a critical process and then a supercritical one. And then we'll talk about what the difference is. We'll look at the equation for it and so on. But as with a lot of things, it's best to start with the demonstration of it. So I think we're going to go ahead and do that. What we've got up here are two sets of dominoes. We're going to play a little bit today in chemistry class. We've got two sets of dominoes, and they're set up in two different patterns. The first pattern is a simple chain. It does have a couple of loop-de-loops in it, but otherwise, each domino is going to hit the next one in our chain. And that will be one type of chain reaction, because once it starts, we're not going to be able to stop it. So I've got somebody here who's going to start the timer as soon as I knock down the first domino. So
I've never seen somebody so
get
bad.
set, go. Okay, stop. And that was 3 seconds. Is that right?
All right.
3 seconds.
So 3
Okay.
seconds. Record
So
that.
that was a critical process. One domino hit the next. So one after the
I don't
other.
like this lady.
What
I
I've
just gave
got
away
here
all
is
my
another
dominoes.
setup of
Why?
dominoes, but this time I've arranged
not
them in a rather intricate pattern. I know, can we see that in the audience well? Can
No.
we focus
There's
on
no
that a little
audience. We're
bit?
not stupid.
Is that good? Can we see that? Okay. And basically what you want to look at here is that, and this basically is, we have this set up on the board, is on the bench top as well. What is going to happen here is that each domino hits two other dominoes. So now we're going to go what's called supercritical. So when I hit one domino right in the middle, it's going to hit two. Those two are each going to hit two, and so on. And so that's going to multiply out. Did we catch that pretty well, do you think? Okay, so if we saw what that looked like, we're going to go ahead and try to time this one. Now here we got to be really good. You got your back down to 0 time. Okay, and I'm going to hit this one right here in the middle, right? That'll be good. Okay, on the count of 3. 1, 2, 3. How long did that take? Not even a second.
Not even a second.
So we had a critical process.
All right. Not even a second. All right. So the critical process took 3 seconds, I think she said.
Honestly, I think we should just discount, because that guy's an idiot.
The supercritical took 1 second. Okay. So dominoes per second. How do we get that?
Divided by 3.
100 divided by 3 is?
3 would be point. No, just regular 33.
So critical, just one after the other, after the other, after the other. Supercritical is crazy, right? One hits another, hits another, hits
That
another.
is crazy.
Are you ready for the last one? Yes, sir.
Is it leaves?
You know, that was my first guess. That was my first guess.
Is
but,
it a bowling ball or is it the moon?
and I looked up and like a leaf can break.
Yeah, but like how often does that happen?
Say what?
How often does that happen with Instagram?
Well, it doesn't have to hit the, like, it just can't break. So what object cannot break? But it always falls. Your car can break.
No, my car doesn't.
Oh, your heart can break.
It's been broken.
All right, we ready for the last one?
Hey!
Yes.
It's dirty.
It's not a bouncy ball. Bouncy balls can break. All right, now this last part gets a little tricky. I'm gonna be honest with you guys. This last part's tricky. It's a little, honestly, it kind of hurts my brain to think about. All right, so the last question says, where does the massive amount of energy from nuclear reactions come from? All right, this is where it kind of all boils down. Where do we get that energy? Where does it come from? How do we use it? Okay, so remember, what's right here? Do we remember the name of this? Hydrogen plus a neutron. That was a deuterium atom, right?
Yeah.
So deuterium creates, what was my product? in fusion, we're back to fusion. What was my product? 4,2 helium, otherwise known as alpha, right? We create an alpha particle, okay? So imagine weighing the separated protons and neutrons before they fuse together, okay? Let's see. Imagine weighing before they smash together, then weighing them after they smash together to form a new nucleus. Okay, so weighing them before and after. The separated particles weigh more than the resulting nucleus. So this weighs more than that. As you can see, the scale is going down.
But it's the same stuff.
It's the same stuff. You are exactly correct. Now, the difference is called the mass defect. That's the difference. It's the same stuff, same exact thing, but the difference is the mass defect. And the difference in mass becomes the amount of energy created. Okay? And this is Einstein's famous equation. Okay. So it's the same material, just different masses because energy. We got to account for energy. So, wait a minute. So they're saying energy has mass now? In theory, Einstein says energy has mass. Crazy stuff. That's fusion. But where does fission get its energy? We good to go?
Yeah.
Where does fission get its energy? Okay. So, a very, very similar concept. Very similar. Okay? Fission, the mass defect. So remember, the mass defect's the difference in mass. The mass defect can be converted into Einstein's equation as well. This is called the binding energy. Remember, fission, right? This is called the binding energy. Is that it? Of the nucleus, and is sorted like a nuclear glue. Okay, so we're going to compare it to glue. Okay. Imagine removing the glue from a giant uranium. So we have uranium. Imagine removing it. Imagine removing the nuclear glue from a giant uranium atom and from the nuclei of the products of fission U235. Okay? So imagine removing the nuclear glue from uranium and barium krypton that hold together. There is more glue in the uranium nucleus than in the glue of all the products. Okay. Basically, it's telling us what this picture shows us. To bind uranium by itself is heavier than binding barium and krypton. So, what is missing over here? Why is this side lighter? What's missing? Maybe energy, right? Can I go to the last one? We good? Last one. The last one is if we convert the mass of nuclear glue into energy using Einstein's equation once again, this is the amount of energy released when the giant atom splits. splits during fission. Wow, there's a lot of missing words in this one. So we were missing energy in our equation. And that's it. Right? So where do we get this energy? Well, we get the energy from the missing mass. Right? We get that energy. Crazy stuff. Do you guys have any questions? How do we feel on those 6 questions? Pretty good? All right. With the last 10 minutes, I want you guys to answer those few questions on there. I want you guys to answer some of those few questions. Now, you guys can work with partners. All right. If you guys want to collaborate or just talk it out. But I want you to try answering those questions. We'll go over the answers here at the end. We'll start our project tomorrow. Okay. Try it out. Yes. Like I said, we'll go over the answers here in a few minutes.
Did you do you do that? I'm losing
No, it's just these guys keep falling down, so I'm just gonna hang it up through there.
More stress. Really like, oh, video. He's actually smart. He's not maybe. I just don't think he looks Does he do that? Yeah, dude.
Oh, that's so much better. All right, take about 2 more minutes. We'll go over these answers. Has anyone ever slacklined before? Slacklined. It's where you have that little line of slack between trees. You walk across it.
I have done that.
Similar, yeah. It's pretty fun.
I've done that. It's not that exciting.
Slacklining?
Yeah.
Seriously? I don't know if you did it right then. There we go. All right, let's go over these real quick. All right, which one requires very high temperature? Very high temperature is fusion. Number 2, the nuclear process is what is utilized in an atomic bomb. That is fission. The nuclear process involves a neutron bombarding a giant unstable atom. That is fission. The next one. The nuclear process does not produce waste. Fusion does not produce waste. Which process involves energy being produced when 2 atoms combine? Fusion. The nuclear process can be critical or supercritical. Fission. Okay. The nuclear process involves 2 heavy hydrogen atoms smashing together. That is fusion. The nuclear process involves energy being released when a giant atom splits. That is fission. Okay. The process is what is used to make energy in a nuclear power plant. That is fission. And the very last one, the nuclear process produces waste. That is also fission. Okay. And then number 2 all the way to the right says, in your own words, describe the fission reaction in a nuclear power plant versus that of a bomb. What would the difference be? Okay, very good. But what is the fission reaction? What's the difference in the fission reactions? So one's bomb, one's a power plant. What's the difference in the reactions? Well, the difference is the reaction, or the chain reaction. Okay? The difference is the chain reaction. A bomb has a supercritical process. Right? Because one hit explodes off another, and it just keeps exploding and creates a huge shockwave. Whereas in a power plant, they use a critical process, basically so it doesn't blow up. Right? So different chain reactions is what the two relates to. How'd you guys do? Pretty good on that? 10 out of 10. Wow. Holy smokes. Kind of crushed it.
Kinda.
All right. Good job, guys. All right, you guys got about a minute. You guys got about a minute. All right, that time's yours. Have a fantastic day.
2 minutes power.
Are we having a graduation? Or are we having? Oh, hey, great.
Just for the QR.
No, I actually.
I was so if you start like the first number you have is a key.
It was.
That's why. So let's say we're solving the POA. So you're gonna lose this equation. So 14 minus whatever. So 14 minus that will give you your POA. That's why you're gonna go up. So you use the up.
How is
You can, yes. So let's say you have the OH number. So here, in this row, you have the OH number. Does that kind of make sense? Yeah. Right. Maybe tomorrow we can work on it.
I install. Got it.
You're good.
Chase Lyons, can you come to the receptionist desk? Chase Lyons.
Good morning.
Bye.